Hey, so the topic today, evaluating limits analytically. This corresponds with section 2.3 in our textbook. So let's say we don't have a table of values or a visual graph to look at. So what do we do without those? Today's notes are all about giving you more tools so you can address more kinds of functions. So think of it as leveling up. You're getting new tools, new skills to address more and more difficult challenges. So some basic limits to look at first. Okay, b and c are real numbers, n is an integer. The limit of b as x approaches c is b. So this is really just generalizing your constant function. Alright, so any horizontal line, the behavior is what the function is. It's not very exciting. It's predictable. Example 2, the limit of x as x approaches c is c. This is just really your linear function. So you have x is approaching c. Well, it makes sense. The limit is then c, because x is approaching c. So your limit is also approaching c. Limit of x to the n as x approaches c is c to the n. So this is your polynomial function. As you have x to the power of n, x is approaching c, so just plugging in c for x. So no longer x to the n, but c to the n. Now all of these use what we call direct substitution. These are all well-behaved functions. They kind of do substitution. Okay, they kind of do what they're supposed to do, what you expect them to do. So evaluating the limit, making a prediction about the behavior, is as simple as plugging in what you want x to be approaching, and then evaluating, because the function is well behaved. There's no surprises, no tricks, no all of a sudden, oh, this happened. It's all very predictable. So predicting is as simple as plugging in what you want x to be approaching. Some properties of limits. Let's say that f and g are functions, so that the limit of x is of x. Take two. The limit of f is L, and the limit of g is k. So L and k we can use as limit values. Your scalar multiple limit, if you have b times fx, go ahead and evaluate the limit of f. Don't forget to scale it up by b. If you have a sum and difference, so f plus or minus g, that is just your limits plus or minus. So L and k plus or minus. Same with multiplication. Same with division. And same with your power. Now, one thing I want to talk about, this came up a few years ago on the exam. You also want to look at limits of composite functions. So when you have f of g of x, so g is plugged into f. Kinda how do you work with that? Alright? This might be better to do this. So the limit as x approaches c of f of g of x. Now remember, evaluating composite functions, you kind of work inside out. So you would plug in the number for x, plug that into g, get your answer. That answer, then plug into f, get your final answer. It's kind of the same thing here. If you want to do the limit of a composite function, try this again. You want to deal with what's inside first. So you want to deal with g of x first. So f of the limit of g of x as x approaches c. Now the limit of g of x is k. So then you'll have f of k. And then you evaluate that, f at the limit of g, k. So for all well-behaved functions, you can just do direct substitution. So for a constant function, here's my box. Limit of 5 is x equals 3. It's just 5. It's a horizontal line. The horizontal line is always 5. For example 2, 4x squared plus 3, limit as x approaches 2. Just plug in 2. 4 times 2 squared plus 3. 2 squared is 4. 4 times 4 is 16 plus 3. Get 19. The limit of x squared plus x was 4 over x plus 1 as x approaches 1. It's all direct substitution. The denominator x plus 1, if you plug 1 in, you'll be fine. You'll have a denominator of 2, so there's no problem. So wherever you see an x, just substitute in a 1. I believe that comes out to 6 over 2, which is more commonly known as 3. Example 4, oh, unicircle. Alright, got to know that, especially at a minimum, you got to know the first quadrant. So limit of sine of x is x approaches pi over 2. See, sine is the y value at pi over 2. You're up top, so the point 0, 1, so you have 1. Alright? So you always want to try direct substitution first, okay? You can save yourself a lot of trouble just trying that. So always try direct substitution first. It might not always work, but you want to try it in case it does. So look at example 5. X squared plus x minus 6 over x plus 3, limit as x approaches negative 3. So, really quickly, try to plug in negative 3. But in the denominator, you get a problem. Negative 3 plus 3, you have 0, and we still can't divide by 0. So what you have to do is a method to evaluate this analytically. That method is called factoring. So if you have a rational function, a top and a bottom and a fraction, the top and bottoms are primarily polynomial functions. You can try factoring top and bottom, then canceling out common factors. So, drawing an arrow, we're not evaluating the limit, we're just going to rewrite the problem. So the limit as x approaches -3, the top you can factor down. Think what numbers multiply to -6 but add to +1. That'd be +3 and -2. And that's all over still, x plus 3. And now, what we have a common factor in the top and bottom. Now, x plus 3 was a problem factor. Direct substitution, it would not let it work. Well, we have a common factor in the top and bottom. The common factor is the problem factor. So we can, quite literally, cross out your problem. You're getting rid of it. So you're left with the limit as x approaches -3 of x minus 2. Your remaining factor. Now your remaining factor is a linear function, x minus 2. Linears are well behaved, so you can kind of cycle back to direct substitution. So -3 minus 2, you get -5. So, does the function exist at -3? No, it does not. Kind of looks like this, okay? It exists. There's -3. It exists again. You know what? Let me do a better graph. I just had an idea. X minus 2. That's a line slope of 1, y-intercept -2. So -1, 2, 3, 4, 5. -1, 2, 3, 4. So kind of graphing it this way, okay? -2, get that, get that, get that. And then at -3, x equals -3, you have an open circle. And then the function continues. So your function looks something like that, okay? It does not exist at -3, okay? So your original rational function, x squared plus x minus 6 over x plus 3, does not exist at x equals -3. Okay, I want to make that clear. The function does not exist. But if it did, what would it be? Now the line x minus 2 agrees with the original function at all but one point. So if you were to graph x minus 2, you'd graph the same line as the green line, but when you got to the open circle, you just fill it in. Alright? So does the function exist at -3? Unequivocally, no. But if it did, hypothetically, what could it be? hypothetically, it could be negative 5. Because we have this linear function, x minus 2, that informs us what it could be. Because x minus 2 and your fraction, they are pretty much the same. They are the same everywhere, except at negative 3. So where the rational function has a hole, doesn't exist at negative 3, the linear function plugs that hole and gives you the missing information. Example 7, if you have a rational function with a square root and a plus or minus something else, we can do what's called the rationalizing method. So this works with conjugate pairs. Alright? So conjugate pairs, they kind of have their roots in imaginary numbers. So if you have an imaginary number, a plus bi, the conjugate pair is just the minus. A minus bi. And what happens is, when we do the rationalizing, we multiply top and bottom by the conjugate pair. So using the opposite sign, root x plus 1, then plus 1 instead of minus, what you do is you introduce a difference of squares into the problem. So when we distribute, take the root x plus 1, multiply it in to both terms, take the negative 1, multiply it into both terms. You're going to get the difference of squares with some terms canceling out. And then your denominator, don't do anything with it, okay? So we haven't evaluated the limit yet. Limit as x approaches 0. So I'm going to write everything out. Naturally, in the future, you're good at math, you wouldn't. But I'm going to write it out for the notes for the first time seeing it. The first distribution of root x plus 1 times root x plus 1 gives you root x plus 1 squared. The second distribution, the root x plus 1 times 1, just gives you root x plus 1. Now the third distribution, negative 1 times root x plus 1 gives you a negative root x plus 1. And then your fourth and last distribution, positive 1 and negative 1 multiplied together, giving negative 1. All over. Now the bottom I'm not going to distribute. Just leave it as x and quantity root x plus 1 plus 1. Okay, so writing everything out. Now, good things are going to happen. The square root being squared, those cancel. The positive root x plus 1, the negative root x plus 1, those cancel. Your plus 1 under the root, your negative 1 at the end of the fraction, those are going to cancel. So all you have left in the top is just that one solitary x. But hey, look at the bottom. There's an x in the bottom that I didn't distribute. Common factor in the top and bottom. More importantly, that's the problem factor from our original problem, the x in the denominator. You try to do direct substitution, plug in 0, doesn't work. But now, the x's cancel out. So we have the limit as x approaches 0. Everything in the top cancels out, so we only have a 1 over root x plus 1 plus 1. Alright, now direct substitution, plug in 0 for x, and you end up with 1/2. So, again, finding a function, 1 over root x plus 1 plus 1, that agrees or mimics or mirrors your original function. And where the original function has a hole, the new one plugs in, fills in that hole. Example 10, limit as x approaches 1 of x over x minus 1. Remember, you have your parent function, 1 over x. This graph has this kind of look to it of a rational function. So we're increasing and decreasing with that bound. We have does not exist. The other examples on this page, you want to look them, work through them, check my completed notes if you get stuck, or to check your answers. And of course we have some trig, alright? So, to really look at trigonometric limits, you gotta look at the Squeeze Theorem, which kind of randomly showed up on the AP exam a couple years ago. We talked about it early in the year. We don't really talk about it any other time. But it does kind of give you some insight into what happens. Let's say you have 3 functions, h, f, and g, and they're all kind of stacked. So h on the bottom, f in the middle, g on top. If h and g kind of converge towards each other, f will also, stuck between them, have to converge. So as g goes down, as h goes up, f stuck in the middle will have to kind of converge with them and get squeezed by them. So then they're all going to go to the same location. Alright? So some special trigonometric functions that we have. A sine of x over x as x approaches 0. 1 minus cosine of x over x. Or flip those numerators and denominators around. You still have these same numeric limit values. So looking at some examples, they might require some rewrites. Alright, from your trig class, you should know that tangent can also be written as sine of x over cosine of x. And that's all still over 1. And then through some algebraic manipulation, sine over cosine over 1 is the same as sine of x over cosine x times 1 over x. Okay, so dividing by 1, same as multiplying. Oh, sorry, miswrote something. This isn't over 1. I'm like thinking to myself, this is not quite gonna work out. Okay, so over x. So sine over cosine divided by x. We don't divide, we can multiply by the reciprocal, so times 1 over x. Sine of x over x is the same as 1. So we have the limit as x approaches 0 of 1 over cosine of x. Direct substitution, cosine of 0 is 1, so we have 1 over 1, which is more commonly known as 1. Example 17. Here's the thing with the limits. Gonna go back here. Sine of x over x. So look in this one. Think of it also as sine of something over that same something. Alright? So not necessarily always x, but sine of an amount over that same amount. Now we have sine of 4x over x. So sine of something over a fourth of that something. Well, in algebra, one of the cool things, you can do anything you want, as long as you keep things balanced. So, we want to get 4x in the bottom, we can do that. Kind of write it this way. What would you do to the bottom? You also got to do to the top. So the limit as x approaches 0 of 4 sine of 4x over 4x. And now you got the same thing in the top and the bottom. And sine of something over that something is the same as 1. So you're just left with 4. Alright? Example 18 also. Take a look at that on your own. Check your answer and your work with my completed notes online.